Got it. All right. Can you hear me on Zoom there, everybody?
Yeah.
Right on. So let's start out on page 175 in my book, or it should be the same page as has question 30.1. And I'm going to make sure this pauses here. Come on, computer. We alluded to this last time, induced EMF. Oh, come on. Sorry, I'm waiting to. As soon as I walk away, it'll start, right? In my book, there. Or it should be the same page. All right, sorry about that. Okay, so I want to talk all day today about induced EMF. It's probably one of my favorite topics. I wish I would have told all of you that are out there on Zoom, this is like probably the best day to be in person. Just because it's, I think it's fun, but we can decide later if you think it's fun or not. I'm going to do my best to show you all these cool demos. But yeah, we'll see. All right, so induced EMF. The equation we discussed last time, or sometimes it's called induced voltage. Sorry, I'm skipping all around there. Induced EMF, induced voltage. The equation that we alluded to last time, it was the time derivative of what? Do you remember? The voltage related to a derivative of what does that symbol mean?
Magnetic flux.
Magnetic flux. Now I want to emphasize, and I cannot stress this enough, it's magnetic flux, not magnetic field. It relates to magnetic field. Does anybody remember how magnetic flux relates to magnetic field? Field going through a plane. What was the physics equation or the math equation?
Integral of B dot dA.
Yes. Right? And then often we assume B external is approximately uniform to simplify this calculation. Now, to show you why I think that might be reasonable, here's a loop. Right? And I know it might not stand out that well, but it's just a circle of metal, right? Now, the idea is maybe if I put a magnet near this thing, like pretend the marker is a magnet and this lid is the North Pole. Well, it might not be perfectly uniform, but it's probably approximately uniform over this size scale. So we're going to make that assumption a lot. It's not true at all, but it's approximately true. So we might say this is approximately equal to B times area times the cosine of the angle in between, right? Everybody okay with that? Dot product might give rise to this. So far, so good? All right. So now, in this case, we alluded to this last time. If I have a loop here like this, I think it stands out if I put it against my shirt a little bit there. Okay. So we have this loop and we have a magnet. The idea is I will get voltage in the loop if I change the magnetic flux. What's one way I could change the magnetic flux? Move the magnet. Which way? Anyway, right? If I move it here, do you agree the flux through the loop has changed? If I pull it back, if I push it through, all we have to do is change the orientation of these. What's another way? Move the coil. True. What's another way? How do I change the angle? What would that mean? Rotating things, right? So you can rotate the loop. So those are the main things. Basically, you can move the magnet, move the loop, or change the angle by rotating something. I want you to kind of keep that in mind. So far, so good? All right. So, I haven't really mentioned this too much, but I want to bring attention to this minus sign here. There's a minus sign here. What does this minus sign really mean? Well, a lot of times when we're talking about these induced voltage, we completely ignore the sign in this part and we talk about a different thing called Lenz's law. Induced EMF, and this is written in your workbook, so you don't have to write this down. I forget what I said. I'll say it this way. So the minus sign is supposed to represent some kind of direction here. And it's this word opposes, right? So opposite, opposes, minus sign, that's where the minus sign comes from in this equation. Now it says the induced EMF tries to create a current which opposes changes in flux. So again, if you think of this loop, and this is being a magnet here, right now, let's say this is a north pole of the magnet, right? The lid of this is the north pole of the magnet. What direction is the flux through this loop? Is it into the page or out of the page? Into the page. So it's almost like we're looking at, well, let's start here. 30.1. 6. There's going to be a before and an after picture here. And the idea is there's a B external. I'll try and draw that in blue. There's my B external. And afterwards, there's only one B external. So you can think of that as me pulling the magnet away from the loop, right? It's exactly the same as this, just pulling it away. What's magical about this is this should try to create current. Now, it's very difficult to understand the direction of like a battery here, but I'll get to that in a minute. For right now, I want to focus on this claim here. Lenz's law. We're going to try to create current which opposes the change in flux. Now, when I look at this picture right here, I've lost flux into the page. Do you agree? We've lost flux into the page. What is the opposite of that? Gaining flux, which way? No. If I lose into the page, isn't the opposite gaining into the page? Right? So in this case, I lost flux into the page. I should try, in an ideal world, the induced EMF, I should say, is trying to put that thing back. I used to have 4 X's going through the loop. My flux used to be 4 into the page. Well, now I'm going to try and change that. Well, the induced current wants to create X's. Which direction is current flowing? Which way? It's either got to be clockwise or counterclockwise, right? And I don't know if I said those words right with my hand motion. So it's either got to be clockwise or counterclockwise. Which one of those would try to create this B induced? Let's see. The idea is the loop opposes the change. It wants to put those X's back. Isn't that clockwise? Yeah. So in this case, we're going to create an induced current clockwise in an attempt to restore the lost flux into the page. So far, so good? All right, hang in there. It'll get cooler. We got about 6 of these, and then we do a whole bunch of demos, okay? Now, look at the next page, 30.2. I'm going to try and put them all on here. 30.2. B external is 2 X's. B external is close. So in this case, It's bringing the magnetic field closer to the loop, right? What direction is the induced current? Well, let's start by analyzing the flux. I increased flux into the page. What is the opposite of that? Decreasing the flux into the page. What's another way to say that? Increasing flux out of the page. Do you agree that creating a dot is the opposite of adding an X? So in this case, if you ramp up the external field, right, the induced B field should oppose that change. Well, so here we see taking away X's, the opposite would be adding X's. It's a little bit different. Adding X's, the change would be adding dots. Adding dots is the opposite of adding X's, or it's equivalent to it. What way is current flow? This way, right? So far, so good? That's what I'm trying to describe when I talk about Lenz's law. So if you have a loop, you change the magnetic flux, right? And here's the thing that students do all the time that you don't want to do. People all the time look at the B field, they'll say, oh, there's an X. Oh, that means the induced current must create a dot. Not always. Sometimes it does, sometimes it doesn't. The induced B field opposes the change in flux. All right, enough on that? Let's go to the next one. 30.3a. All right. Let's call this. And we probably need to scoot over some. Okay, so in this case, B external starts as 2 X's, ends up as 4 dots. What are you going to try and do in that case, right? We had it like this, right? So I have my loop is here, here's my magnet. What am I doing in this case? How do I get this other field here? What am I doing with the magnet probably? You could flip it, right? Watch this. When I flip it, it's not only closer, but it's also the opposite pole, right? And so that's why we see, you can imagine just flipping it like this, it's going to get closer and go the other way. All right, so what's the induced current? What am I going to try to create? Dots or X's for the induced? What is it? X's. How many? 6. So what direction is the current in this case? Clockwise, same as this one, right? The induced current matches the induced B field. Which one of these do you think has the largest induced current? 1, 2, or 3? Which one has the least? 2. So this is where that d phi dt comes in, right? So if you recall, the induced EMF is proportional to the change in flux. So the direction, this minus sign, has to do with this Lenz's law crap. So the direction of the current is what am I adding X's or dots? And then the size of it depends on the amount of X's or dots that you change. So this would be the size of the current. This is like the direction of the current, so to speak. Good enough? All right. Well, all right. So that's good enough on that. Let's try this one. Whoops, 30.4. Actually, I'm going to do this on the other board. This one might surprise you. Let's do it this way. I love this problem. Actually, yeah, let's just do it. All right, it's not a great picture here, but the idea is, let's say I take that aluminum ring and I cut a slit in it. I know this seems silly, but just trust me, we're going to build off this all day, okay? So I apologize if it feels like it's going too slow here. It'll pick up. We're going from no to some B external. Is this a loop in which current could flow? What do you think? There's a break in it. What do you think? How about on Zoom? What do you guys think? You think we could ever get current to flow in this? What's in between this gap here? Can air conduct electricity?
With a high enough voltage.
If you apply enough voltage. So I'm going to be a little bit ridiculous here. And I'm also going to keep standing in front of the class too. They're not mutually exclusive. I'm going to put some resistance here. It's approximately infinite, right? So you're right that we wouldn't expect a lot of current to flow, but do you agree if you change the flux enough, you might get a lightning spark here?
Yeah.
So in that sense, this is a complete loop. It's just got an extremely high resistance. It's extreme. All right. Good. All right. If we could push current, which way would it flow? If you could push current, which way would it flow? Let's see. For the B external, we've added dots. What's the opposite of that? I went from no dots to 4 dots. What should the induced current try to do? Take away dots, but we can't take away dots, so we have to do the opposite of adding dots, which is, yeah. So that would be the attempted B induced, but do you agree we would not be able to actually produce that B induced? So we expect B induced should be approximately 0 because resistance of air is approximately, whoops, infinity. But what direction would be the induced current then? Clockwise or counterclockwise? So we expect an I induced, which is approximately equal to 0. Agreed? So now my question to you is this. Here's the fun part. We could still induce the voltage. We just don't get the current flow, right? Mm-hmm. Which side of this resistor is positive or negative? You understand the question? You saying this side's positive? What do you think?
Right side's positive.
Why do you think the right side's positive?
Current flows in the opposite direction of the electrons.
Well, okay, we're trying to understand this as a circuit. Do you agree? I'm going to model a circuit here. This is my favorite. Okay. Now, in this case, do you agree it's basically the same thing as this circuit, but just rotated 90 degrees? Okay, so there's the resistance, the air gap right here. What direction is current flowing through that resistor if it actually existed? This way, right? What is the source, the power source in here? The chunk of metal. The chunk of metal is like the battery. What direction is current flowing in the battery? Towards plus terminal from minus terminal, right? This is the battery, right? Well, I know that inside the battery, current is flowing towards the plus terminal. This is the plus side. You see it now? Isn't that trippy? Think about it this way. Isn't a current a flow of electrons the opposite way? Shouldn't those electrons pile up over here and get stuck and leave this side residual positive? Isn't that weird? I don't know. I find that fun. I don't know. Questions on that? All right. I think we got 2 more of these and then we'll get to the demos. All right. Hang in there. Any questions from Zoom? Does that make sense? Kind of ish?
Sounds good.
I like that. I like that attitude. All right. Let's move on here. I just find this one interesting. Usually every year somebody asks about it. Somebody asked about it in the morning class, so it worked out for them. But at 6 at night, nobody cares anymore, right? All right, so. All right, so let's do 30.5. This one's a little bit different. And you just got to trust me. It's going to build all day today, all right? We're doing something different here. I'm changing the size of the loop. Originally, we had a small amount of flux. And then what's happening here is, let's say there was some current flowing here. Now, I want to be clear here. This is B external. And this is, I'm going to call this IAP for already present. The idea is maybe there's a battery that we're not showing, but there's some current flowing in this wire. When you flow current in a wire, if you flow enough current, you agree it's going to heat up and expand? Okay, so let's say it heats up and expands. Now, obviously, the resistivity would change too, but maybe we made this out of a special wire whose resistance does not change as it grows. Remember, we could talk about a carbon nichrome composite wire. Whatever. Okay. What do you think is going to happen here? There's going to be an induced current as well as the already present current. Agreed? What direction is it? Let's see. No. We've added field out of the page, haven't we? So don't we need to create a field into the page to cancel this out? What direction is the induced current then? Check this interesting fact out. We see that if you're running current in a loop, that loop will heat up and expand, which will, if there's a magnetic field present, you're going to put in a current that tries to oppose the current that's heating this up. It's going to try to cool it back down and shrink it. It's physically opposing the change in its growth. Weird, right? Now, we're going to see a number of these situations. Here's what's going on in here that's a little bit different. I want to point out a subtlety here. These induced currents can never truly counteract everything. Just like in this one, right? The resistance in the loop itself is usually enough to cause these induced fields to be very small, right? In certain cases, they won't be, and we'll see that in a minute. However, the other thing I guess I should say is these induced currents also only last while the flux is changing, right? So what's going to happen is if you heat this up, it's going to grow, and then at some point, it's going to reach a maximum size and stay at that size. Once it stays at that size, there's no more induced current. Whoops. I just want to point this out. At some point, these things stabilize. Once they stabilize, the flux is no longer changing. The induced EMF goes to zero. The induced current goes to zero. Is everybody okay with that? Again, these induced currents, I would say, are transients. They're very short-lived. So they try to oppose the changes, but then they don't succeed, and then things stabilize. Is that okay? All right. Try 30.6a on page 177. Look at my claim, see if it's plausible or not. All right. Go to it. I'm going to erase the board. 30.6a. Talk with your neighbors or whatever, or chat in the whatever Zoom chat. Okay. Is this possible or not? The B field's out of the page, but current's running the wrong way, isn't it? Is this plausible? What would be a plausible before picture? What's that? 8 total dots? Okay, let's see. How about I say 9, just because I have 9, all right? So what you're saying is, if we start with B external being large out of the page, then we come down to this. What would I be trying to produce with B induced? I lost dots. If I go from 9 to 4, wouldn't I need to be creating dots? That would need a current this way. That doesn't make sense. So this doesn't work. Does that make sense? So what would it have to be then? Okay, you could do, or just no field, right? The idea is now, if I go from less dots, then I would have to create some kind of an X, right? My induced field. All right, so it's possible. So far, so good? Now, last time, I told you guys to come up with an explanation for this thing. Remember that? Showing up. Oops. Let me fix the keyboard. All right. That'll wake you up, right, Nick? All right. So. Okay. So to be clear here, we've got a solenoid. It's connected to power. In this case, AC power. Right? There's an iron core here. So it's just a bunch of piano wire put together in some plastic, shrink wrapped. So we have a nice strong iron core. This is called soft iron. It's easily magnetizable, which means it's highly susceptible to a change in magnetic field. Right? So it magnetizes easily. When I turn this thing on, whoa, the ring goes flying off, right? What's up with that? Can you explain it to me? There's no battery here. Huh, yeah. maybe, just maybe, we could look at question 30.7. How about it? Should we try it? Shall we go for it? Okay. All right. You guys, did anybody know that reference? You probably don't. Sorry, man. You're just hurting, aren't you? I saw there was this is gonna sound strange. I love this clip of Ariana Grande on Jimmy Fallon singing like kids songs in the styles of like Celine Dion. Have you guys seen this one? Whatever. Check it out. Shall we go for it? That's her Celine Dion impersonation. Just cracks me up. $30.7. I'm going to start with the solenoid here, and you notice I kind of skipped the part D, right? So the idea is there's going to be a solenoid, and there's a ring around it. This is the top view of this thing, all right? And we're going to try and talk about before and after. The idea is, right, you're looking at this. I don't know if you can see that at all. The idea is the solenoid is this central core. It's causing the flux. We start off this. There's a current in the solenoid. I'll call it I sol. What direction is the B field created by the solenoid? Right? We're going to grab that solenoid. What direction is the B field? Into the page. Oh. Now, because this piece of aluminum is concentric with that, what is the induced current direction in the coil? In this aluminum ring. Same way or opposite way? Opposite in this case, right? Because we went from no to X's. What is the induced B field? A dot, right? So by turning on this coil, we're going to cause a current flowing the opposite way as the solenoid. All right. Now, if I drew this from a side view like this, right, from the side view, the current's flowing this way in the solenoid, and there's a B field up. That's the external B field. Then you have your ring here. And the current's flowing the other way, right? What direction is the magnetic moment associated with this induced current? Think of the magnetic moment as the B field associated with this loop. Which way? It would be, wait, did I go the wrong way? Uh-oh. Oh, what did I do wrong here? This one's wrong. Do you see it?
Oh,
shouldn't this B field be down? Yeah. I'm a bad person. I didn't grab that coil right. I think the B external should be down. Sorry about that. That means this one has a mu up, right? Well, think of mu, the magnetic moment of the coil, as being like a bar magnet, right? Think about this. This solenoid is not quite like a bar magnet, but kind of, with its north pole facing which way? Like that, right? Now, how about the magnetic moment? That's like a little bar magnet with its north pole facing which side, on top or on bottom? What happens when you put a south pole near a south pole? That, right? Now it's a little bit more complicated than this for two reasons, right? This gives an idea of the initial force. This is pretty good for getting the initial force. However, it ignores a couple of factors. One of the factors that it ignores here, that's pretty cool. It's like right on top of it. One of the things it's going to ignore is the fact that this is AC current. And I could show you this. There's a weird effect here. So instead of spiking it, I'm ramping it up. And notice the ring starts to levitate here, right? So this is not explained by this phenomena right here. So there's two things that we need to learn. One of them is the concept called inductance, which we're going to learn about later in this chapter. Oh, that's so cool. All right. The other, just going to remind you of something. Take a look at problem 28.21 in your workbook really quick. It's on page 147 for me. I'm just going to let this keep going here. Yeah, it's getting really hot, really painfully hot. I can still touch it, but barely. Oh, there you go. Watch out, it's hot. Oh, no, it's not that hot. You can grab it and then just let go of it. It's not like going to burn you or anything. Right? Do you agree it's pretty warm? Yeah. It's pretty hot, right?
Oh, right.
It's hot, but it's not like burning you hot.
Don't be scared up here. Get that contact.
So I guess I'll say it this way. So if you really want to understand this, right, the magnetic field from this is warped. And so if you want to understand the forces on it, you could do problem 28.21. And then we'd have to factor in AC currents, which that's in chapter 31. So the next chapter problem, I think it's 31.7. We're going to revisit this. Let me see, what does it say there? Yeah, we're going to come back to this on 31.7, and I'll give you a journal article if you're really sick and want to read it. All right. All right. So far, so good on that. All right. Now I got this one. Let's see here. I don't know how well this one's going to show up. Maybe we'll just do this. I got these. I got this tube here. Need to scale. Give me just a second on Zoom. I haven't forgotten about you. Is this too easy for you guys or not? Or is it too hard to tell you? Yeah, it always gets hard at the end, right? Good.
Oops. Fine.
Okay. Actually, I'm going to scoot this back a little bit. All right. Now, make sure they can see it on Zoom. And I'll probably erase that background so it's not so messy. Let me get this. Let me erase this crap. Okay. Make sure that holds up. And we can get this solenoid out of the way. All right. In this case, just want to show you this. I got these two tubes here. Yep, that's hollow. How about this one? Yep, it's hollow. Do you agree? You don't believe me? Can you see through those pipes? Hollow?
Yes.
Nothing tricky? All right. All right. So I'll just do this. Just drop something through there. Yep, still hollow. Drop something through this one. It's still hollow, but this one, did you see that? Can you see that on Zoom at all? Watch how long it takes to fall. This one falls right away. This one, still in there.
Is it possible to move the camera down just slightly?
Yeah, we'll zoom in and show you the output here. Okay, so.
Yeah, that's all I can't see is the bottom.
Yeah. So I can't show you the top and the bottom at the same time. That's max, right? So watch it right here, right? 1 banana, 2 banana, 3 banana, 4 banana, 5 banana, 6 banana, 7 banana, 8 banana, 9. About 9. Did you see it fall out?
Yeah.
Okay, so what the heck is going on here? Why does it take so long? This is not magnetic. This is, right? You see that? This is steel, this is aluminum. How is it possible that this magnet is taking longer to fall through aluminum? What's the story? What's that?
Magic.
Magic? How about problem 30.8? Magic or the next problem in the workbook. I think this is cool, but you guys are totally tired or something, right? All right. So let me try and draw this over here, okay? So on your next test and probably the final, I usually love to throw in something where I ask you about these induced currents, just so you know here. I'm going to try and draw 2 current loops here. What I'm going to try and do is draw it dotted on the back. It's really hard to visualize these. So the solid lines on the front, the dotted line is supposed to indicate the back side of the pipe of the tube here. All right, now we got a magnet. Which way did I draw the North Pole on this magnet? Top or bottom?
Top.
Top, thanks. What direction does the magnetic field go near the North Pole? Out or in? Out. And do you agree it's going to be kind of warped like this?
Yes.
Now, if you don't like these pictures, well, I guess don't read the solution. Wait, that's wrong. Which way does it point near the South Pole? In. Like this? I'm trying to draw this the best I can. Now, which way does it point near the South? In. Does the magnetic flux through each of these imaginary loops change? What direction is the induced current on this top? Remember, this is supposed to be the pipe. I know it's kind of hard to visualize, but should I go like this or should I go like this? The second one, why? I lost upwards flux. So the field is up, and because I lost upwards field through the loop, because I lost upwards flux, I need to put it back. Excellent. So we expect an induced current on the top this way, right? Trying to put back some of that lost upwards flux. How about on the bottom one? What's that? The other way, because I added too much upwards flux. Make sure they can see this. Yep. All right. Well, now let's try and do our magnetic moment trick. What direction is the magnetic moment for this one? It's the same as the B field direction. Yeah, so that's mu top. How about this one? Mu bot. Well, now what we can do is we can try to visualize this thing as a bar magnet, even though it's not really like that. This should be a north and a south, which corresponds to mu up, right? Is this killing you? You can always take off if it's too much. I understand. The other one's flipped upside down, right? So I want you to think of these magnetic moments as like little bar magnets, okay? Now check this out. Does it make sense there was a force that slowed down the magnet? What happens to this North Pole relative to that South Pole? Is it attracted or repelled? Attracted. South on south? Repelled. So what's happening is, as the magnet falls through this piece of aluminum, it's inducing currents all the time that oppose the change in flux. And so when it first falls through here, right, this section of the loop has got a current one way, and then as it falls, every single section of the loop has an induced current in it. So if you have a large enough magnet, right, these rare earth magnets, you can actually get it to take forever to fall through. And in fact, I heard you say acceleration, so now we got to talk about it. You fool! What should be true, right? Do you think this thing is hitting terminal velocity or not? Well, let's check. That's pretty darn fast. That's not. Agreed? So it's probably hitting terminal velocity. What does terminal velocity mean? Acceleration zero. So you're telling me that the acceleration is equal to zero. What are the forces on this? Give me one force acting on this magnet. mg. And then there's got to be a force upwards. We're going to call it force magnetic braking. As in the brakes on your car, right? If we're at terminal velocity, what should be true about the braking force versus mg? They should equal. Now, I happened to measure this thing earlier today. It turns out the mass is approximately 25 grams. So I need somebody to look carefully at this scale right here. Zoom, you're out of luck here, or maybe not. I'll try and show it. Let's do it this way. Let's see if we can zoom in on that scale. You can kind of see the scale there, right?
Yeah.
Now, you want to stand up and see this? Can you read this? It's pretty still right now. Try to read the number. What do you think? In grams?
Roughly like, oh, in grams? 800 something.
Maybe like 820?
Yeah.
Would you say it's just over 800?
Yeah.
Okay, so now I got to put this in here delicately. Wait till it comes. What's it at now?
Like
About.
a little less than 850.
About 850, right?
Yeah.
Keep watching it. Now it goes back. Do you agree?
Yeah.
So this corresponds to the mass of that. So we're seeing that it really does hit terminal velocity here because the scale is only attached to the pipe. Now, how do I know that that's true? Well, think about it. If the pipe is exerting this force on the magnet, what force is the magnet exerting on the pipe? The same by Newton's third law. So the idea is this is an upwards force on the magnet, but the braking force is exerted downwards on the pipe. So you're not getting something for free. We're actually seeing the force. Isn't that cool? Yeah. Slightly cool. All right. Now, could you see that on Zoom at all?
Yeah, a little bit. Couldn't see the numbers, but I got the idea.
Okay, yeah. All right. Hopefully the scale moved a little bit.
Yeah, I saw that.
This is like the workout day. All these demos are really heavy. All right. let me clean up the back of this whiteboard a little bit. All right, I have two pendulums here, right? Maybe if I turn it this way a little bit, you can see. All right, and this is just a really big magnet, okay? I should be careful here. This is not something to kid around with. I think you can kind of see that a little bit. All right, there we go. Now, I'm going to pull these up and hopefully not hit the microphone. Okay. They're not behaving exactly the same. Do you agree? One of them's almost stopped. The other one has not. Why? How about, well, let's see if it's just friction. Maybe there's friction. If I take this magnet out, right? They seem pretty similar. They're not perfect, but they're pretty close, right? They're maybe getting out of phase. They have a slight different weight, but they're, do you agree they're both? So clearly the magnet had something to do with this. Do you agree? Right? Here, there's slight differences in the mass, so we're getting some phase. But they're both staying approximately the same amplitude, right? Okay, try it one more time. Why is one of them slowing down and the other one not? To me, it's pretty dramatic that the magnet is having an effect. Can you tell why? What's the difference? Slits. What was the deal when we put a slit in the ring? No current, right? So the idea is the slits in this ring break up the eddy currents, right? So all of these currents that we see, these induced currents, are sometimes called eddy currents, right? This one can have a huge eddy current because there's no slits. This one can only have very small ones, right? The slits basically break up the eddy currents. And so as a result, we see less magnetic braking. Could you use this magnetic braking for anything? Or, I mean, this seems pretty contrived the way I'm demonstrating it, right? Do you think it could actually be used for anything useful? What's that? Yes, you could use this to stop trains, right? So yeah, or roller coasters or things like that. So one way to think about it is, I'll just kind of exaggerate this here. So the idea is, imagine this is a rail that a train sits on, okay? Train track. Are we on the right Zoom screen? Yes, right? Now imagine the train, right? Here's the wheel of the train somewhere. And then right over here, I'm gonna make a solenoid. But you know me, I'm gonna make it doubly wound. Oh yeah, doubly wound. B external outside is 0, except for right here. The idea is I can energize this solenoid and create a B field, right? And then as a result, I could induce eddy currents in the track. Which way? Like that, right? And then what happens is, just like the magnet falling down the pipe, you go to a different spot of track. In theory, if you have enough magnetism, you can stop a train with this thing. It seems crazy. Look this up later and see if I'm folded. If you want to understand this problem, I think it's a good one to kind of walk through. This is 30.9 that we just looked at, the eddy current pendulum, right? Are there, I don't know. Can you think of any other applications here? Have you ever seen this in the real world? Let's do some examples here. So I'm going to bring this up here. Go to demo land. Oops. All right. Here's an application. Electric toothbrush, right? You recognize that? What do you think that thing is right there? A chunk of what metal? Probably iron, right? Doesn't it look eerily similar to this? Right? Is it on screen? Oops. Here we go. The idea is, here's a chunk of iron sticking out, right? Wireless power transfer. You can charge stuff this way, right? Here's another example. This is pretty terrible. Right, but maybe you've seen one of these before. There's a magnet inside of there. Now this is poorly made. We made it homemade, but right, you can imagine there's a light on top, right? Maybe you've seen it like this. You change the flux through the loop. When you change the flux through the loop, you can charge up a capacitor and get some light. So if you rapidly change the flux through the loop, the light might last a little longer, but yeah, it's totally terrible. All right, so this is a cool emergency flashlight you could use. You could change the flux and use that flux to charge up a capacitor and use the capacitor to light an LED. Your batteries never go bad. Maybe a good emergency flashlight for a car or something. Here's another example. Right? Microphone, right? This is a crappy microphone. We can abuse it. I'll pass it around. If you look closely, there's a ring. And that ring is attached to a plastic diaphragm. You can hear it wiggling, right? The idea is the sound from your mouth can cause pressure waves, which cause the plastic to wiggle. That causes this coil to wiggle to and from a magnet to induce a current. Same thing as pickups on a guitar. Oh, that's kind of interesting. Take a look at that for the phone. I got another one for you. Ready? I just keep throwing stuff at them. Just we wake up, right? Here's a weird application. What is that thing? Can you tell? You guys see it on Zoom at all or not? Does it need to go up?
I can see it, yeah.
I can raise it up if you need it. But, all right.
We're looking at the plastic tube, right? With the,
Yeah.
yeah, okay, yeah, I can see it.
You see there's a spring in there? Right. Now I have over here. I personally think the applications of this are so cool. That's why I'm going to show it to you over and over. So apologies if it's boring to you, okay? What's that? At this thing here.
Yeah.
Yeah, just give me a second. I gotta plug it in. I'll throw it at you. Yeah, it's cool if that's what you want. That's right. That's right. I got to keep you awake. One time I used to work nights when I was going to school. And oops, I got to turn this on. It takes like 2 minutes to warm up here. And you know, having to work nights and go to school in the daytime, it was rough.
Yeah.
It lowered my GPA like a full point. But yeah, or at least half a point. But it's just hard when you know, these night classes. I don't want to be teaching them either, but that's what I got to do, I guess. All right. So what's going on here? We've got this device here. There's some magnets in there. Do you see that?
Yep.
And there's a coil of wire right here. And it's on a spring. This coil of wire is attached to this weird connector. Now this device is called an oscope. Can you guys see the oscope on Zoom? Let me check.
Yeah.
Yeah, you can. So the idea is I want you to think of this as basically a DMM on steroids. It reads voltage. You know this. So it reads voltage as a function of time. I want to make sure I get this set right. Okay. So now, what do you, any guesses? So I can read the voltage as a function of time here for this magnet near a coil of wire that's got a spring on it. What is the name for this device that starts with the letter S? Seismograph. Oh, it's not gonna wiggle enough. Let's put it on something more. Oh, man. Oh, there, here. Oh, it's an earthquake. Here, let's do it this way. Watch, if I wiggle it up and down, you see the voltage changing? And when I let go of it, it stops. There's my homemade earthquake. Yeah, you want to try it? Let's do a Nick quake. Let's try to jump up and down right next to it. Ready? You are not Marshawn Lynch. Anyways, okay. But yeah, so yeah, we can find a better place to do this, but yeah, all right, you get the idea. It, in theory, could measure earthquakes. That's a cool application of this. And then I know you're tired and want to get to your break, but I want to do one more here. I want to revisit this jumping ring and see what you think about this, okay? All right. So give me a second. Oh, geez. You guys like all these demos or not? Is it more fun than regular class or not? All right, because it's a pain in the ass. Guys, if you don't like it, I'm never doing it again. I like this stuff too. I don't know why. Okay. Let me see here. We got it. All right. So this one, the reason I like this one is because I have some various rings we could try out with it. So we got our ring jumper demo, right? Okay, here we go. This is going to be our reference. You ready? So class, you got to watch quickly. Okay, one more time. See it jump? About right there, right? Now, I don't know if you guys can see that at all. Oops. Okay, now what I'm going to do is I'm going to use this ring here. So I want you to look at it. Same dimensions except for the height. What do you think would happen? Will it jump higher, less high, or the same? What do you think? Why do you think less?
I would have put like I actually said to go higher, but then I'm like, physics is like the opposite.
Why do you think it would go higher then?
Or something surface area.
Well, is there more mass?
Yes.
Yes. Do you think that would help it go higher or make it lower? So, okay, so we expect that it's heavier, so it should be harder to make it go upwards. So, but do you agree it goes higher? But why does it go higher despite weighing more? Yeah. You agree we must be somehow getting more induced current? Yeah. Well, let's look at this thing. Whoops. Can you see that on the whiteboard, Zoomers?
Yep.
Yeah, okay. That's a picture of it, right? Which direction is the induced current flowing? This direction. It's either this way or that way, right? I don't know. Let's just assume it's, sorry, bad question. Let's assume the induced current is flowing this way. I just meant it's not flowing up, right? It's going around it, or, right? You know what I'm saying? We expect the induced current should be flowing around the loop. So if you double this thing and make it twice as tall, should that make it easier or harder for current to flow? Easier, right? Do you agree that this dimension right here, this is the cross-sectional area? By doubling the height, you double the cross-sectional area, you reduce the resistance. So it's actually easier to make this thing jump. What if I put 2 of them on here? Really goes up. What if I use copper instead? What do you know about copper versus these aluminum rings?
Doesn't do worse.
Which is a better conductor, copper or aluminum? So based off that, what do you think should happen to the copper? So then what do you think is really going to happen? It's going to go lower. Why? Well, you can hear it. What's true about the copper?
More dense.
More dense. Pick it up and weigh it. You feel it? It's like crazy dense. So you get a 20% increase in conductivity or something like that, or a 20% reduction of resistivity, but you get this massive increase in mass. So make sure they can see that too. Pass it around. All right. What's up with this one right here? Why is it not going anywhere? What's that? No, it's aluminum. What do you think? Why isn't this one going anywhere?
Dwarf physics.
Oh, the old split the aluminum ring trick. Okay, jeez. Isn't that so dumb? Now, let's go back to our original one. Let's say I want to make this one jump higher. Right? How can I make this one jump higher? Can you think? Give me a way to make it jump higher. How can I get more current? I can't. Need more current. What's that? How can I make it more conductive?
Heat it up.
If you heat up metal, what happens to its resistance? So then what do I need to do? Cool it down with some dry ice. Now, let's do it this way. Oh. You're gonna like this. Oh, that's cold. Very Halloween-esque. So I'm just gonna cool this thing off, freezing my fingers in the process. All right, so we're getting this thing nice and cold. All right, now it's pretty cold. You agree it went higher?
Yeah.
So this corroborates what we're saying about the resistance matters. Agreed? Is there a practical application of this?
Yeah.
What? A light bulb. The idea, I can really see the light bulb go on when you got there. There's some kind of joke there. But the idea is this is wireless energy transfer. So up till now, it's kind of been seeming pretty silly. Last time, didn't we talk about this as being a way a generator could work?
Yeah.
And we'll show that in just a second. But the idea here is you can actually transfer power from one object to another. So one of the biggest applications of this is wireless energy transfer. Have you ever seen one of those things you put your phone on and it'll wirelessly charge? What do you bet? There's a couple of coils of wire and some iron in there somewhere, right? So yeah, that's kind of interesting. And to that end,
Overlap making a wireless charger.
all right. Whoops, wrong one. Give me a second, Zoom. I haven't forgotten about you. This would have been a fun day to be in class, huh? All right, so I'll just pass these around here just so you guys have these to look at. We've got some different motors and generators here, right? And I just want to show you, this is a motor. Whoops, oh, where's the Zoom? I have no idea where the camera's at. Let's go. There we go, that's pretty good. So we've got some different motors and generators, and I just wanted to point out, you can actually turn these things and see what they look like and get a feeling for this, right? And you can put it in DC mode or AC mode here. You can see what happens to the lights, but I just wanted you to compare a generator versus a motor and see what they look like. The main difference is the input to a motor is electricity and the output is kinetic energy, it spins. Generator is the opposite. The input is kinetic energy We're gonna do this one in a second. The input is kinetic energy and the output is light. So you could try the AC DC. So I'll pass these around. And since we've got it here, I've got a jumbo one. Motor. All right. I need a volunteer. You want to try it out? Come on up. Switch sides with me here. Zoom, can you kind of see this thing?
Yep.
All right, so this right here is a DC motor. We just pulled out of something. I don't remember what. This used to be an exercise bike that we just tore the crap out of. And then when you look on the back here, you can see this right here.
Yeah.
There's just a bunch of light bulbs wired up, and we've got some switches. You could turn them on or off like this. This switch is messed up, so we have a jumper wire. We could just connect the switch manually if we have to with this jumper, right?
Yeah.
So if we need to, we'll do that. We'll just leave that there for right now. All right, so let's turn all these off. That one doesn't matter because that's crap. Okay. So now in this case, ooh, let's dim the lights to make it mysterious. It's kind of Halloweenish. All right. Oh well, Nick, you're probably gonna wake up now. You got a car headlight right in your face.
I'm thinking about it by 2020 vision here.
That's right. No, don't worry. It's almost impossible to get anything. So, all right. So I want you to grab that pedal and just turn it as fast as you can. Going. Hey, we got it, right? You see some light? Okay, go ahead, stop for a second. Now we're going to add another one. Try it again. It's starting to go, right? Okay, let's see if you can get all three. Oh, that's pretty good. Can you short that across the switch there? Just grab any part of it that fits. Okay, this is going to be really hard. Ready? Go for it. Go, go, go. It's almost impossible, right? There it goes. Yeah, he got it. Nice. Let's give him a round of applause here. That's like the quietest round ever. What's that? Yeah. Okay. So the idea here, the reason I wanted you to see this one, these are old incandescent bulbs that were used from automotive, right? And it's just, it turns out you could really, isn't that exhausting?
Yeah.
It's like, just to get a little bit of light, this is to remind you to turn the lights off when you leave your bedroom. Right? The idea is it takes so much energy to get these going. Good thing we have LEDs now, right? But it's not easy to create all this electricity that we use all the time. So make sure you take care of it. All right, that's it. Yeah, question.
Oh, no, okay, shouldn't it be sound like the first one? People pedal it.
Well, we used to have a bike here, but it's tricky because this is usually what we use for the kids, right? And so then it was hard to get one that fit all the different kids. But yeah, it's pretty fun to watch people try to exercise riding this thing. But if you try this thing out, right? Man, it's just so exhausting because you have to go so fast to get anything. It's not like there's a lot of resistance, but you just have to keep going so fast. Obviously, if we wanted more light, we could use a different motor, right? So we could try and have more magnets. And that might make it a little bit easier, right? But when you're giving this to kids, you want them to struggle and suffer. So that's why I don't know, hopefully that was kind of cool. How did those demos turn out on Zoom, people? Could you see any of that or was it horrible?
Yeah, it looked fine.
You could
I
see.
probably should have come in person, but
Yeah, I didn't think about that, whatever. That's all right. Tell you what, it's 6 o'clock. We need a break, agreed? Let's take our break. We'll come back here and we'll do some more. Maybe we'll talk about this in more detail and how we get these AC currents, etc. All right. these demos out of lightweight aluminum. Be a little easier, but everything here is just iron. Maybe what I'll do is I'll leave these demos on the cart, and then after the talks, if you want to see them in person live, we'll have them. All right. So those of you that are on Zoom, you can see them in lab. Oh my goodness, what a mess. Oh. This is that. Any questions while I'm just getting organized up here? Basic concept that ties all this together. Changes in flux are useful. All right. That's the main thing we're trying to get out of this today. Clean it up after class. What's that? Yes. It's always good to have a hot ring to throw at students that are falling asleep. Yeah. Use dry ice to cool them off. Cool your jets. Cool your jets, Rob. Talking about these, talking about that. Kind of lecture now. Dry ice and bubbles. All right. Ooh, I need that. Kind of good. Okay, where were we? Is it time? I hope it's time. I don't even know anymore. What is time? Oh, okay. All right, so let's do this. I want to skip around a little bit. What do we got? 30 minutes left. You can make it. 35. Where is that problem I want to do? I'm going to skip around a little bit. I want to talk about page 184, problem 30.19. We discussed this last time briefly, and I might need to bring up the simulation again. So while you're reading that problem, let me bring that up. Is this the new one? I forget which one's the new one. All right, we're going with this one. That's what I remember. As well, do is I'll share screen. Booting up, I'll bring it up here. This one. That's firing up.
Magnetic field?
Okay, so hopefully you guys can see this up on the front really quick. So we're revisiting this one. We know that the magnetic field near bar magnet goes out of north and into south. Great. Here we have a pickup coil. So this is what we started with today, right? You bring a magnet close to or away from a loop, and you should see a transient spike in current, right? It's a very brief current, and we see it spike up there, right? So the idea is if I just leave this field here, there's a massive flux through the coil right now, but it's not changing. It's only when you change it, when you bring it in or out, that we see something. So let's go up here to the generator. Now, in this case, we could apply some force to a magnet on a pinwheel and cause it to turn around. Now, at this point, I want to This is not exactly the same thing as what we're going to discuss in 30.19 for one major reason. This is a bar magnet. Is the field near a bar magnet uniform? Is that uniform? No, it's like changing in intensity and direction all over the place, right? So this is an approximation here to, we're going to make an approximation in a minute. But in this case, I want to try and walk you through this right here. Now, I'm going to step this thing forwards, right? So one increment, one time step. When I do that, do you think the magnetic flux through the loop will change a lot or a little bit? In particular, maybe I'll annotate right here, right? We know that there's a B field kind of going into south, right? Sorry, that's crappy. There's a B field into south. A second later, or one time step later, will it be a dramatic change in flux? What do you think? Will the magnet change positions dramatically in one time step? No, it's going from, it's basically like we're saying, look, initially you're just below, afterwards you're just going to be just above. But do you agree that it should be approximately the same magnetic field? Yeah. Right, so let's clear these. I'm going to show the field, right? Let's do one time step. Look at the flux through the loop. It doesn't change that much. Do you agree? What do you notice about the light bulb? Is there a lot of current or not a lot of current? Is it lit up or is it no light? Right? So when we watch this one, the thing that's a little bit counterintuitive about this is we actually get the smallest, right? We actually get the smallest amount of current when the pole face is directly towards the loop for this scenario. And that's because the changes in, even though the field strength is greatest, and even though we have maximum flux, we have a minimum change in the flux, right? All right. So if I want this to be brighter, I could speed it up, right? So we get a lot more light here. That's cool. We're getting a lot of flux. We could actually jack up the loop area to trap more of the flux. We could use larger number of loops, right? The number of turns affects this. And so the idea is you can get, we can jack up the size of the magnet too, right? So if we want maximum amount of light, we want to have this thing rotating quickly. We want to have it close to the loop. And we want to have large number of loops with a large area capturing as much flux as possible. There's a trade-off in the real world though, right? If you make your loops a larger area, what happens to the resistance of the loops? What's that? If you use a larger loop with the same number of turns, what happens to the total length of wire? It gets longer. What happens to the resistance of the loop? You have to drive current through a longer wire. It's more resistance. So there's a trade-off here. You may get the same, you may get more EMF, but you may get less current depending on the situation and blah, 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 blah. All right. So this is what I want you to have in your mind as we go to, whoops, problem 30.19. Just kind of keep that visual in your mind. That's what we're trying to talk about here. All right. And we are on this board. So try to visualize this. We're going to go through the women's NBA again. You remember that? We've got a loop here. And then there's a B field out of the page. Is that right? Yeah. Thank you. So there's an external field this way. We're going to put an axis of rotation here. All right. Now, in this case, this is a side view. I think it would help to have a top view, and that's why I drew one. The axis is now that dot. If we look at it from a top view, the axis is a dot. And in this case, we could see this thing as it's rotating through some angle, I'll call it theta. So the idea is we could actually see the rotation better from the top view. If you're looking at it from this way, it's really hard to see the rotation, right? Can't see it that well. Now, I want to understand the electricity inside of here. What equation do you think I should write if we're trying to understand the electricity associated with this magnetic field and loop? What's the equation we've been saying all day? Or part of all day? What is this equal to? Minus n. And to be honest, a lot of times what we do is we just like absolute values on here and then figure out the direction with this right-hand row. So yeah, okay. Well, we're going to assume B is uniform, all right? We're going to simplify ours. We're going to assume B external equals uniform. So we don't have the same complications as that simulation that we just saw. Well, if the B field is uniform, how can I rewrite this equation? What was the equation for magnetic flux? Yep. To be clear here, we want to make sure we're using the right angle. Let's talk about the area vector. What are the possible area vector directions for this rectangular loop? What's that? Into the page or out of the page? Which one do you think seems nice for this picture? We could choose. I like out of the page. There's our area vector. So now let's try and view it from the top. If we're viewing it from the top, we have B external this way. You guys good or no? All right, that's fine. That's fine. Okay. The area vector is going to be this way, right? Do you see that the angle between it also happens to be theta? That's what I was trying to stress here. That's it. Good. We're told that this is rotating at a constant rate, omega. How does that get involved? What's that? Well, how does theta relate to omega? What's the equation for kinematics again? Let's do x. What's the equation for delta x in physics? Delta x equals the initial x t plus. What's the equivalent for theta land?
And that'd be what, omega t plus 1/2 alpha t squared.
Yep. Now, we're told this thing is rotating at a constant rate, right? Alpha goes to 0, omega initial equals omega. So theta is just omega t in this case, right? So I could put that in here. Is the B field changing over time in this example? How about the area? Is the loop changing size?
No.
No, the direction is changing, but we're accounting for that with the dot product, right? Remember the flux came from B dot A, so there's a, okay. So when I pull all this out, minus N B external area of the loop times ddt cosine omega t. What's the derivative of cosine omega t? What? Oh, don't call it W, even though we want to call it a W. Remember, this is omega. So let's make that clear. This is omega, not W. Yeah, you did change it. Okay, so what do you get when you take the derivative of cosine? Negative sine. We get a minus sine of omega t, and the chain rule times the derivative of what's inside. I'll say d theta dt, which is omega. So that's where we get the minus signs drop. I hope I'm on the right way. The minus signs drop and we get omega n b. These are all the factors that we just saw in that simulation. You remember that? You can change the rotation rate, the magnetic field strength, the number of loops, the area of the loop, right? These are the factors that we saw in the simulation that could affect it. And after all that, you get a sine omega t. Now, you know me, when I see something like this, I'm going to want to plot it. Who wouldn't want to plot this? What's that function going to look like? Sinusoidal, right? So this is T, and this is EMF, or the induced voltage, as a function of time. Can do something like this. Now, so our example is a little bit different than the one we saw in the simulation, because ours was using a uniform B field, and theirs was kind of non-uniform. The idea here is, what is this amplitude here? What's the amplitude of this function? WNBA, which we really know as omega, but it's easier to remember as W. Okay, so this is going to be the amplitude, and it's a sine function. So this would be omega n BA. So that's supposed to be, all right. What application does this have? The electricity coming out of every wall socket on Earth? Possibly. The voltage is sinusoidal. Isn't this cool? How do power plants work? Well, how does a hydroelectric plant work? Right? You use falling water, or I would say fluid, right? And you cause a magnet to turn near a loop of wire, and we get electricity out. How does a coal-fired power plant work? You heat up some water, turn it into steam, and it spins a turbine. Connected to the turbine is a magnet. How does wind power work? Wind is turning the magnets, right? How does nuclear power work? Nuclear power provides the heat up the water to make it boil, turn it into steam. So you do that, or you can do liquid sodium. What's the popular type of power production that doesn't use this principle? Solar. Solar works on semiconductors and a different principle. But this is a huge, huge result, right? So if we want to understand AC power, we've got to understand this. All right, what do you think about that? So far, so good? All right. We should do another one, huh? Oh, do I really want to go into this? Oh, man, we got a full day next time. Oh. I don't know. You guys are beat. You guys are tired. I don't know. Do you guys, is this too easy for you guys or what do you think? Any questions? I think it's cool, but I think people are pretty cashed, huh?
Completely lost on what anything is, but like it looks cool.
Yeah. Well,
It doesn't help that I missed like all like 29, so like this, which builds on this.
yeah.
So like, I'm like completely lost, but like it's really cool. It's really cool looking at it.
Yeah, all right. So you just need some time to look at it. All right.
Yeah, I just need time to catch up.
How about you Zoomers? How about you questions? Questions from the Zoom scene? Do we have any Zoomers still awake out there?
I'm here, but I'm good. right
Yeah.
now.
Yeah, no questions. All right, I think probably we might as well just call it a day, because what do we got, 5 minutes or, oh, no, wait, we still got 15.
Yeah,
Or we got 20, oh, I was misreading the clock because of the glare over there. I couldn't see it right. I thought we only had 5 minutes left. We can still got plenty of time. All right, sweet. So we're gonna plow through it. Oh, okay.
Wait, here's another question.
Yeah.
So the big difference between this and DC power that is a magnet power? That's called thing like 2G.
So a DC power, I like to think of as battery power, right? So there's chemistry that produces dissimilar metals plus chemistry causes electron transport, right? And so in this one, it is changes in magnetic flux that causes electron transport, right? Electron transport is current, I guess. Call it.
I do. What's like the general like, or like the power sources people usually kind of vary between like DC and AC. Is there like advantages to doing one versus the other, or?
Yes. Why? Okay, so this is a good question, right? AC is more likely to kill you. It's less safe. So especially at 60 hertz, which is approximately the rate at which your heart beats, right? So then why would we do something more dangerous?
Usually more dangerous stuff has like more usefulness.
Or it's cheaper, right? People like to do things, right? People are willing to take more risks to save money. Unfortunately, that's the way it is. So, okay. I haven't really talked about this, but we're talking about it now. Let's go to page 185, transformers. All right. So let's take a look at, it looks like for me, it's problem 30.20. A lot of that is basically words. Give me a sec. And maybe what I'll do is I'll bring up my simulation again. I got it right here, so give me a sec. Bring it up on here. It starts up. Erase the board really quick. I'm going to try to understand transformers. So Nick said there's got to be some reason we do this, right?
Yeah.
And so let's talk about that reason. And it's going to take me a minute, but I promise to get there. And the claim is it saves the power company money because they don't do it for us. They do it for them. All right. I mean, think about, because constantly, have you seen these power supplies at your house that use AC to DC converters and the big ugly power supply, right?
Yeah. Put on like your car.
Yeah, we're constantly having to use AC to DC converters. So, and there's a project, I believe it's up at Cal Poly that you can get involved with called DC House, right? And it's just building a DC house, right? Basically a battery operated house, which is pretty easy if you have a solar panel, right? You can have inverters, but why not just have everything run off DC? Well, let's take a look at this. All right, now you're really gonna fall asleep, right? Okay, so here we go. Do you agree I have two solenoids here? Do you see them?
Yes.
Two coils of wire, all right? Now what I'm gonna do is I'm gonna bring this other solenoid closer here. While I'm moving it, did you see there was a brief transient current?
Yes.
And now it's gone, right? I'm not seeing any current through the light bulb. But what I could do is I could use AC power. Now in this case, as it oscillates, you see a small current there. Do you agree?
Mhm.
And do you see the B field constantly changing?
Yeah.
I could jack up the amplitude to make this more dramatic, so I get more B field, or I could even increase the frequency. So we see this, and I could bring them closer together and literally put them right on top of each other. So hold on a sec. Sorry that's so cramped in there. Let me make this loop area bigger so I can move them apart a little bit. All right. So in this case, we're seeing this huge amount of energy transfer. This is the wireless power transfer that we were just talking about a minute ago. Look at the electrons inside the wire that is connected to the light bulb. If I draw, maybe it will help. I'm talking about these electrons here. Do you see them oscillating back and forth? Give it a minute.
Yeah.
See it?
Yeah.
Sometimes they're going on, right? So the idea is the induced current in the loop is opposing the change in flux. And what we see is, if I switch to DC, I don't get this happening. Well, this is a transformer. When you're basically transferring energy from one coil over to another. The number of turns in each coil relates to the voltage. So I could actually do this. I could use fewer coils here. I could use one coil here and 4 over, oh, whoops, 3 in this one. So now when I do this thing, if I switch it back to AC, right, I'm not producing as much B field, but I'm also not, I'm also getting more out of it. So the idea is, all right, let me put these things a little bit apart. Let me step this up to 2. All right. So the idea here is we have 2 terms, and actually all right, give me a second. Oh my gosh, that's slow. Okay, I'm going to move this over here. All right. Move closer. These were written in Java, and I have to use a simulator to run them now or something like that. All right, so I want to call this thing here, I want to call this the primary. So I'm going to put a P. This loop here is called the secondary. All right, and the idea, the number of turns in the primary is usually called N subscript P. And that's going to relate to the amount of magnetism created by the primary coil. The number of turns in the secondary will relate to the N in the EMF. So EMF in the secondary should equal minus N in the secondary times d phi dt, right? I promise to get to something useful. Just hang in there. So the idea is the magnetic flux is created by the other coil. All right, so far so good. So why does this save the power company money? Well, let me show you here. Let's go to the whiteboard. And let's go this way. Let's go here. And this one is, yeah, sorry, I should have warned you there. Okay. So the classic example of a transformer is you can enhance the magnetic flux transferred by using a square loop of iron. It's soft iron. And it's much more complicated than what I'm going into here. So I'm just going to gloss over. Oh, let's do this. We have some iron here, all right? The iron is useful, just like we saw in this example right here. Right, the iron core here, this is killing me today. The iron is easily magnetizable, but it amplifies the magnetic field and it traps the flux, right? So this, we like to say that the flux, the magnetic flux is trapped. So if I come in here with a wire and I wrap around like this, and I connect this to an AC power, something like our generator that we just saw a minute ago, right? I'm going to create a magnetic flux that's up, then down, then up, then down. And what I could do is I could come over here. One, two, three, four, 5, 6, 7, 8, 9, 10, 11, 12. Right? The idea is I could have 12 turns here. So in this particular example, let's say the number for the primary equals 4, and the number for the secondary equals 12. All right? And in this case, we're going to make the assumption that all of the magnetism created by this solenoid is trapped and pinned by the flux and goes through the other solenoid. So this very efficiently transfers flux from one side to the other. And as a result, we're going to make the assumption right now that we lose negligible energy. Okay? And you might lose 3 to 7% depending on how it's built and thermal and blah, 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 whatever. But the idea is the output over here, right? This should be an AC output, right? And let's ignore the starting of the sine wave, whether it's positive or negative and stuff like that. Let's forget about that. So the idea is we're going to get a voltage, an induced EMF versus time that looks like this. Now, the claim is, and let me get this written here, delta V2 over delta V1 should equal the ratio of number 2 over number 1. And I guess we could rewrite this with secondary and primary here. So 2 means secondary, 1 means primary. So maybe I'll color code this to make it stick. What's fundamental is this term here, it's called gamma. It's the turns ratio. All right, hopefully I had that in there. Gamma, fish swimming down.
That's good.
What's that?
That's like, I thought it was a different letter.
Yeah, gamma, fish swimming down. Right. Now, in this case, what is our turns ratio in this particular example? What's our turns ratio? 3. So in this case, what does that tell us about delta V2 versus delta V1? 3 times bigger. So delta V2 equals 3 delta V1. We're assuming the voltage gets stepped up. It's called a step up transformer. But wait, there's more, Batman. I said this is going to lose negligible amounts of energy, right? That's the whole point of building these. You try and design them to waste negligible energy. Well, what should be true about these two powers? They should be the same. Isn't power the time derivative of energy? It is. Wait, how does power relate to voltage and current? Poison? IV. I1. I'm not going to write the delta. I'm a bad person. Shame on you, Rob. Shame. I've finally given in to laziness. There should be a delta. Oh, let's do it. I can't help it. Can't help it. All right. Well, wait a minute. If the voltage goes up for number 2, what must happen to the current? So current goes down. Do you agree that I2 should equal 1/3 I1? And now we've set the ground. You could finally address your question. Okay. I want to imagine a scenario like the one shown on the bottom of page 185. Problem 30.21. I'm going to go over here to it. We can come back to this. My claim is this will help you understand your question. Young grasshopper. I know, right? I'm tired, man. We have a power plant. And then this is what transformers look like. Usually they look like coils next to each other in the schematic. We have transmission lines here. And we have another transformer here. Then we have grandma's house. But she doesn't need a chimney anymore because she's got all this great electricity. All right. All right. So the devices in your house are like resistors here, right? So we can just imagine there's some resistance of your house. We call this R load. I don't want to explain impedance yet. So this right here is a step up. This one here, step down. And you've seen these around the neighborhood, right? Have you seen these on the telephone poles and stuff like that? See these big cans looking there, they're transformers. Okay, Nick, tell me why this is a good idea to save the power company money. What happens when you step it up to the current? Current goes down. How do we account for waste? What is wasting energy as this transfers down the line? Heat. How does that relate to the current? How does current? Okay, so you're talking about power and we're talking about current. Write power in terms of current. Yes. Now think about this. What happens when you step it up and the current goes down? What happens to the power? It goes down. So by using AC power, we can use transformers. We can step up the power, drop the current, lose less energy transmitted to the house, then step it back down, and you can still have all that current to do useful work. That's where you save money. You waste less money and heat. So if you jack this up to like 10,000 volts, super high voltage that can kill people, you put it higher up and hope they don't touch it. And then you save a little bit of money, but you still charge them the same, right? That's what the power company is going to do to you. But they waste less, so they make more profit. What's that? You got it? Well, just get solar, right? But it's this large upfront cost. This is how the world works, right? If you have enough money to pay for your own solar system, you don't need to do this anymore. But who can afford 60 grand up front or whatever, 30 grand, depending on what you need?
Well, the power company that invests in solar, so now I'm also the solar company.
Ah, good, good. I was just gonna like become magic and make briefcase full of money, but that hasn't worked for me yet. All right, does that kind of address your question, Nick? This is why we use AC power, because it allows us to use transformers and allows us to waste less energy over transmission over hundreds of miles. This is a big deal. It's kind of hard to explain and it takes a bit of time, but that's why we care about transformers.
Like a distance, sort of like a distance kind of thing. It's like over long distances, AC current would be more viable. Over like shorter.
Yes,
distances, DC
short
more practical.
distances DC. So within a house itself or within a van, right? You just do DC power within a car, right? With cars are DC.
Yeah,
right?
you don't have to worry about energy loss because usually you're like right there.
Yeah, exactly. So, but over dozens and dozens of miles, I don't care how big, well, the cables, right? You can only make them so large, right? Because of the weight. And then they fall down and then they light the state of California on fire. So that's a challenge too. But then you're like, why don't you dig them underground? Because that's pretty expensive too. So there's all these realistic cost trade-offs when it comes to building power systems. Oh man, now we really are done. All right, let's call it a day, huh?
Start early and now we talk about this. Now start late, you know, on time like usual.
Yep, there we go. You mean late like usual? Yeah. Only 2 minutes late. That's cool. All right. Zoom, question on that? I think that's a really, this is one of my favorite lectures. I'm sorry you guys are kind of tired. It doesn't have the same energy when there's only 4 people in class, does it? It's like torture for you guys.
What's the current thought?
All right. Well, I'll tell you this after your talks. I guess I'm going to tell you now. I have the last 3 weeks in the can already. So I'm going to send you links to all these videos and stuff, and you can pre-watch them. And I'm sending them to you so you can pre-watch them or watch them over Thanksgiving break, or do whatever, right, study on your own schedule, I'll still be here. But you can watch them in advance or watch them and then come to class and see them again or whatever, right?
We have Thanksgiving break of 6, it's like 2 days.
Well,